Okay, so this is our last problem in sections 5.3 and 5.4. This is example number 5, and we are looking at torsion and shear stress that comes along with that, and angle of twist and power. And so we've kind of done a little bit of everything with these examples, and we're going to just look at power out. So we have a solid steel shaft from D to F. It has a diameter, so we have a diameter, and that should say 25 millimeters, I think, but it doesn't really matter. So we're going to go with 25 millimeters. So our radius then is going to be 25 over 2, which is 12.5 millimeters. And that equals C. And then if we put that in proper units, okay, it's going to be 12.5 millimeters divided by 1,000 so that we can get it into meters. So 123.0125 meters. Smooth bearings at D and E is coupled to a motor at F, which delivers our power. So our power is equal to 12 kilowatts. And I'm just going to call that 12 times 10 to the third watts so that I don't get confused. And while it is turning at 50 revolutions per second. So we are turning at 50 revolutions per second. We are removing at A, B, and C, we are removing 5 kilowatts, 4 kilowatts, and then 3 kilowatts. So if I'm coming in with 12, so I'm coming in with 12 here, okay? So we have 12 kilowatts coming along here. And then I'm going to be removing 5, which means I now have 7 kilowatts that's going from B to C. And then, okay, and then I'm going to remove 4, so I'm down to 3 kilowatts. And then I remove 3, so this last little segment has 0. So that's how we're pulling out that power, and so that's going to affect our torque that we have. So this is going to be 12,000 watts. This is 7,000 watts. This is 3,000 watts, and this is 0. So now we just need to start working on we have the power, we have the rotation, so we need to get our torque. And I'm just going to start like I always do in terms of unit conversions, and I know that that is 1 revolution. And that's the same thing as 2 pi and 360 degrees. And I need to get it into radians. So if I have revolutions, then I can multiply this by 1 revolution is the same thing as 2 pi, and I've now successfully put that into radians per second. The other conversion I need to make is what is a watt? Well, a watt is, the nice thing about this unit is that a watt is a Newton meter per second. So we're doing great on our units. So if power equals torque and rotation, then our torque equals power over rotation, and we're just going to look at units. So if I'm looking at torque from F to C, then I have my power of 12,000 watts, which is 12,000 Newton meter per second, okay, divided by my rotation of 50 revolutions per second, and I need to get rid of revolutions and put it in radians, so 2 pi. So we are going to be left with units of Newton meters. So I have 12,000, 12, 1, 2, 3, enter, 50, enter, 2 times pi as a number, times, and then divided by, I get a torque of 38.2 Newton meters. And now I can do the torque from, so I went from F to C, from C to B, equals, and we have 7,000 Newton meter per second divided by 50 revolutions per second times 2 pi. And so I'm going to get 7,000, 50, enter 2 times pi as a number times divided by, and I get 22.28 Newton meters. And then the torque from B to A equals 3,000 We already know the units are working out right. And then 50 times 2 pi, 3,000. 52 times pi as a number times divided by, and I get 9.55 Newton meters. So if I were to draw a torque diagram as we're going down that shaft, and I have D, I have A, I have B, I have C, and then I have F or E, whatever, it's all connected in there. Put the D on top so it looks more consistent. So now I can draw, well, what does my torque look like? So my torque is in Newton meters, and I have 38.2, and then I have 22.28. So we're all positive, or doesn't really matter, but, and then 9.55, and then 0. So if I want to know the absolute maximum shear stress, because it's the same shaft all the way down, I know that my maximum shear stress is going to come from this segment CE or CF, whatever we've been calling it. So what is shear stress? Shear stress is TC over J. So I have the torque of 38.2 Newton meters, and I was given a radius of 0.0125 meters divided by pi over 2.0125 meters to the fourth, and I get a nice maximum shear stress of, so we have 38.2, 0.0125 times pi as a number to divide it by 0.0125, enter to the fourth time divided by. So I get this very large number, and remember that's in newtons and meters. So we're going to move it over 1, 2, 3, 4, 5, 6. So I have 12.45, and I've moved it over 1, 2, 3, 4, 5, 6. So we're at a mega Newton per meter squared, which is a Pascal. So our maximum shear stress is coming from that last segment right by the motor. And then it says draw the torque distribution. We did that. The shear stress distribution, so it's going to look similar. The largest is going to be here of 12.45, and then it's going to come down and then come down because they're all the same size. So we're not going to find those numbers, but we would just substitute these values in. And what did it say? Oh, shear stress distribution. So as I'm looking at, well, how is that shear stress distributed? It's solid, and it's going to look like a pinwheel. And if we are here where the largest stress is occurring, it is 12.45 megapascals. Now, if I were to draw it here, it would have smaller values of shear stress as we going down. How would I find that angle of twist? Well, remember phi equals the sum of TL over JG. And we don't have lengths because I was just like, let's just talk about this. So I would go with each segment, I would have 0, and then I would have, okay, I have this torque of 9.55, so I would have 9.55 times the length of AB over JG plus 22 points, oh, you guys can't see that, sorry, 22.78 times the length of BC, and so on. So I could just take these, once I get these torque values, then I can just go through and sum up, and they're all positive, so they're going to be added together. So that's the nice thing about making sure you're keeping up with, is it positive or negative? And we would just sum that up.